So we're going to do things a little out of order probably when we teach 7.3, which is the logarithmic function section of the chapter. And actually what I want to do is go back even further, and I want to graph, this is an old concept, I'm going to graph it, the exponential function y equals 2 to the x power. So 2 to the x power, I could either type this on my calculator or just manually plug in some numbers. 2 to the negative first power would be 1/2, which is 0.5. 2 to the 0 is a 1, 2 to the first is a 2, and 2 to the second is a 4. So if I go ahead and plot these points, I'm going to get an exponential growth function, which I kind of already knew based on the base. There we go. And a couple of, oh, wait, missed some points, okay. Alright. A couple of attributes of this function. Just if you're curious, the y-intercept is at the ordered pair 0, 1, which is where it crosses the y-axis. And then the asymptote, the horizontal asymptote, because it hasn't been vertically shifted at all, is still at the y-axis, which is, or the x-axis, excuse me, which is y equals 0. So the domain for this particular function, and every growth and decay function, was negative infinity to infinity, and the range of this particular one starts at 0 but doesn't actually hit 0, so it approaches it with a parenthesis on the interval up to infinity. So that was an old concept of graphing an exponential growth function. So what we're going to do today is we're going to look at what's called a logarithmic function, and they're going to feel awfully similar when I start looking at this, because it turns out that exponential functions are just inverses of logarithm functions. So a couple of properties that we're going to remember about inverses. They are reflections across the line y equals x, which I could graph this in nicely, that'd be good. So imagine reflecting this shape over this line. That's what we're going to see when we graph this. All the x's and y's switch, so we're going to notice that this and this column are just going to flip-flop around. The shapes look really weird, and it turns out our graphing calculator, while it can graph certain logarithms for us, it doesn't really do a very good job. So what we're going to do is we're going to look at his, relative, the exponential growth or decay graph that we can graph very well, and think about reversing the ordered pairs, and that's how we're going to come up with the logarithms. And frankly, I'm just going to give you ones that you can use your graphing calculator for. The problem we're going to run into is your graphing calculator makes it appear like it doesn't look correct. So we have to kind of be smarter than the calculator. Remember, another property is that your domain and range are going to flip-flop when you have an inverse function, and pretty much everything changes. So if it's y equals 0 for a horizontal asymptote, we're going to end up with what we call a vertical asymptote. Instead of y equals 0, it'll be x equals 0. So if I take all those attributes and I kind of put them over here, remember our ordered pairs were, let's see, if I remember, it was negative 1, 0, 1, and 2 used to be my x's, so now those are my y's. And then the x's that I originally found that were y's, let's see, this was a 0.5, this is a 1, this is a 2, and this is a 4. So basically all I did was I took this table and I rewrote it into this table where I just flip-flopped the x and y. So if I go ahead and plot those points, 0.5, negative 1 would be like right there, 1, 0, 2, 1, and 4, 2. And if I graph this on my calculator, which I wouldn't be able to do because I don't have a button for it, but it's going to look like this. But we have to realize that this part here, this what we're going to call an asymptote, this is a vertical asymptote this time, it does come down and skate along the vertical asymptote line. So just like earlier in the growth question we had a horizontal asymptote, in logarithms we're going to have a vertical asymptote. We'll label it, that might be smart. Vertical asymptote, which is at the line x equals 0. And then you're going to notice, just like the other one had a y-intercept at 1, this guy has an x-intercept at 1, which is the ordered pair 1, 0. And remember we talked about domain and range switching, but I can see that very clearly in the graph here. The domain starts at 0, but doesn't get there because of the asymptote, and then goes to infinity. And the range this time is down and up forever to negative infinity to infinity. So, weird, huh? Like, if I knew what the exponential growth of base 2 looked like, I can easily come up with the logarithm of base 2. So, let's talk about, these are back to your notes, I think. So, if you're looking at your notes page, it's at the end of the lesson. We're actually going to start graphing, I think, when we teach this. The vertical asymptote is located at x equals, and I'm going to call it x equals h, because h is going to be from our formula in a moment. But in this particular example, notice there's no h, right? It says x minus nothing. So we're going to have a vertical asymptote at x equals 0. The x-intercept in this particular case is going to be at 1, 0. But it could be shifted, so we'll talk about that more later. Transformation, let's just write the transformational form down. I think that will help us. Y equals, and then you can put an a in front of any function, so logarithms included. We have log of some various base. We'll talk about what the bases mean in a second. And then it's x minus h, just like every other function we've learned, plus k. So again, horizontal and vertical shifting, same as always. The domain is going to be from your vertical asymptote to infinity. So for us, it's going to be located at the h value, because that's going to move a vertical asymptote to infinity. So for this particular example that we're going to graph right here, it's going to go from 0 to infinity. Oops. And the range, which is going to cover over my screen here, goes from negative infinity to infinity, and that's going to be an always this time, right? Just like the domain for exponentials were always negative infinity to infinity, here the range is always negative infinity to infinity. So just like when I was graphing growth and decay, I'm going to draw my vertical asymptote line with a highlighter. I'm going to plot whatever I need to plot, and depending on what order we teach the lesson in, if you have a logarithm with no base written down, we assume that it's a base 10 logarithm, which means we do have a button on our calculator. And it's a couple above the on button. It says log. That's abbreviation for logarithm. So I want to show you what it looks like on your calculator when you graph this, and then we're going to see why your calculator might not be the best tool when it comes to graphing logarithms. So it's logarithm, base 10 logarithm of x, and when I hit graph, it makes it seem like the graph itself like truncates and it stops. But it's just basically a problem with the pixels. It's not able to plot any more points. Like it runs out of digits basically for plotting points. But we have to know that there's like a vertical asymptote right here, and this little tail comes down and scoots along the vertical asymptote like it did with the growth and decay on the horizontal asymptote. The problem is your calculator's not going to show you that part, so you're going to need to know. So this tells me if you know what your logarithm graph even looks like. And of course we can always go to our table to get points. Get rid of that for a minute. If you go to your table, again, we're going to have an issue with, because we're having it autofill, it's not going to give you a bunch of little points that are close to the asymptote. It's going to start giving you errors because it jumps from integers for the x's. So if you want more points that are closer to the asymptote, you're going to have to switch to either a different counting variable for the change in the table, or you can turn it into ASCII mode, and you could just type in like x equals 0.5, x equals 0.25, but it's probably not worth your time. Anywho, we're going to be graphing this as best we can, which for me is not going to be very good. But I would have stolen some points off my table, and there weren't many to steal, unfortunately. So, when x equals 1, this is 0. Really wasn't much, was it? I think the next point is 10, 1. So, from here we just have to kind of fudge in the shape. Oh, geez. See, I didn't even do that right. So what we're going to do now is we're going to pretend that I graphed that really well, which I did not. Logarithms are very difficult to graph. So when I am grading your graph, I'm going to be looking for you to highlight the vertical asymptote and locate it. And then plot a couple of points, and then just the general shape. As long as you're close, we're gonna call it good. So, all right, here, if you could take a guess, you might be able to understand how this logarithm graph was shifted. It's still a base 10 logarithm, but this one was shifted. Remember, there's opposites with the h, so it was shifted left 1 unit, which means my vertical asymptote, instead of being at x equals 0, is now going to be over here at x equals 1. So for Algebra 2, what I would expect you guys to do is to go to y1 and type in the common logarithm, which is the button for logarithm, of x plus 1, and then you're going to be able to pull a couple points off your table. Let's see. 9, 1. There we go. Not a bunch, though. And it's going to look very close to the one we just attempted to graph, but gosh, that's ugly. This one has been shifted left 1. So again, I'm going to be looking for that highlighter line, and now I'm going to expect you to be able to answer all these. The domain, instead of starting at 0, because the asymptote shifted, now starts at -1, but doesn't get there, so there's a parenthesis. Range is always negative infinity to infinity. Oops, ugly. And the vertical asymptote is now located at x equals -1 because of that shift left one. Alrighty. We're not going to do end behavior for logarithms, by the way. If you're looking for end behavior, you're not going to find it. Alright, this shift of +4 outside of the logarithm function would be an up 4 shift, which does not change the location of a vertical asymptote, because that just is going to shift the function itself up 4. So if I were to type this in my calculator, and then I would make sure that I would close my logarithm function before I hit +4. Let's see, this point got shifted up 4, and then 10(1) got shifted up 4. So once again, I'm going to try desperately to make this ugly graph. They are not supposed to flatten out right here. Mine appear to be flattening out, but that's just a limitation in my artistic skill. Alright, the domain is still, because the vertical asymptote has not shifted, 0 to infinity. Range is always -infinity to infinity for logarithms, and you can't see it in your screen, but the vertical asymptote is still at x equals 0 because it was not shifted right or left any. So everything we knew about exponential growth and decay is just different, you know? Alright, so here, we have two shifts. We have a right 2 and then a down 3. While those are both interesting, only one of them actually moves the asymptote, and that would be the right 2 shift. So instead of being at x equals 0, now that vertical asymptote is going to be at x equals 2. The down 3 shift does change things. It changes the location of all the ordered pairs that I originally was going to plot. So like that original graph that had a ordered pair at 1, 0, it was shifted right 2 and down 3. And then the other ordered pair I keep plotting is 10, 1, and that was shifted, good luck, right 2 and down 3. Yeah, somewhere there. And then again, it's like they get uglier and uglier the more I graph this. This is not supposed to happen that way. Okay, so when I grade yours, I'm looking for you to highlight and close off the asymptote line so you don't go through it. A general shape that kind of resembles that. Yuck. Alright, the domain, now that I see it's been shifted right 2, shifted everything right 2, including the domain, so 2 to infinity for domain. Range is always -infinity, -infinity to infinity, and the vertical asymptote, instead of being at 0, is now at x equals 2 because everything was shifted right 2. Again, don't worry about end behavior, we're not doing that. Alright, so that should give us enough examples. We will be just graphing problems that you can get calculator assistance on, so common logarithms, or eventually we'll find out about the natural logarithm, which is the other logarithm button on there. It's possible to graph other types of logarithms, like logarithm base 2, base 3, base 4. It takes a little more skill, because you got to graph his exponential buddy, and then flip-flop everything. We're going to do more of that in Math 4 and in Pre-Calc next year. But for Algebra 2, we're going to stick to just the common logarithm. This is just the first part, or one of the parts of our lesson for 7.3 logarithms. The other part of the lesson discusses all the manipulations and transformations and inverses of the logarithm function itself.